Hello all, in this lesson we will be studying electric currents. We have a little bit of stuff to go over beforehand though. We have to talk about the units for that, conditions that are necessary, what is conductivity, and then we'll get to some math, which is resistance and Ohm's law, and any factors that affect the resistance of a conductor. The first thing you need to have written on the second page of your notes today is the homework assignment. So copy down this heading as the first thing in your second page, and this aim. How does charge flow and what affects it? That is the thing you'll write down second. And thirdly, please copy down these do now questions, but we'll answer them in class, so leave some space to answer. All right, electric current. Electric current is the rate at which charge passes a given point in a circuit. So do we think that electric current is a vector quantity, and why? So current does have a direction associated with it. Generally, currents will flow from areas of higher potential to lower potential. We'll get to that later in the lesson. But different books will disagree about whether current is scalar or vector. Our book says that it's scalar, but I've seen many books that say it's vector because currents do have direction. And the reason why our books say scalar is because the actual direction of the current is really up for debate. It has to do with the positive charges and the negative charges, and our book is going the route of saying that the direction it could be defined either way, and so they say scalar. But don't be surprised if you hear somebody say vector in the future. But there's no debate on what an electric circuit is. An electric circuit is a closed path along which charged particles move. This is something that you're definitely going to need in your notes. So a switch is a device that we use to close or open the circuit. So you noticed earlier when I discussed circuits that it's a closed path, meaning it's like a complete loop. But the switch is a device that basically just allows you to open and close the loop. So like here, this is a switch. You can see right now that the loop would be open, but if you move the switch down, you would be able to complete the loop and current would be able to flow. So here's a region-style diagram of a circuit, and it's two different configurations. In the first one here, you can see that the lamp, which is here, is not lit. But in the second version, the lamp is lit. Why isn't the lamp in the configuration to the left lit? So the reason for that is that the circuit is open. The switch has been open, so the circuit is not closed, and you need a closed circuit to conduct electricity. One thing that we have to avoid when we do any kind of electrical work is allowing the current to flow too quickly. We actually will install devices that purposely slow down the current, because if you let the current get out of control, it can overheat and catch fire. So we install these things that are called resistors, and they do exactly what they sound like. They resist the flow of current and they slow things down to prevent overheating. Resistors have a symbol that looks like this, sort of like a Charlie Brown stripe. And there are these things called variable resistors. Examples of them are dimmer switches, and you might have some in your house. Dimmer switches will make the resistance be able to go up or down. So for instance, if you turn the resistance all the way up, the lights go dimmer, and if you turn the resistance down, the lights get brighter because the current is able to increase. So the first thing I'd like to introduce involving current is its unit. The quantity or the symbol that we use is a capital I. I'll explain that in a minute. But the amp is the unit for current. So like here's an equation for current. This I is saying that current is equal to the change in charge, which is going to be measured in coulombs, over time. So specifically, it's saying that the current itself is equal to the coulombs of elementary charges that pass a given point in a certain number of seconds. So coulombs and seconds. So amps are equal to coulombs per second. All right, so I said that I would explain the I. I ended up looking this up because I've always wanted to know why current would be measured as, or would be symbolized as an I. So current was named for some work that was done by a French physicist whose last name was Ampere. And we named the unit for current after him, but also the symbol as well based on his work. He used to call current something a little bit different and very French. And the French way that he would say it was intensité des courants, which would translate in English to intensity of the current. So the I is actually standing in for the French word intensité, which we would mean is intensity. And the unit is ampere, which is his last name. So intensité des courants and ampere, that's where those come from. We do have devices that are able to measure the intensité des courants, and they're called ammeters, which is just a device that measures the amps. So they're symbolized like this with an A inside a circle along a wire. And let's put this equation to good use down here. A total of 20 coulombs of charge pass a given point in a conductor in 4 seconds. Calculate the current in the conductor. Well, I know that the intensité des courants is the change in charge, or the coulombs of charge that pass a given point in a certain number of seconds. And they say in the question that it was 20 coulombs of charge that passed the given point. So 20 coulombs, and the seconds were 4. So 4.0 seconds, which means that the intensité des courants is 5 coulombs per second, or 5 amps. Probably the best answer. So that's how you do that. I'm going to let you guys do this one, and then I'll come back and explain. But first, solve. A wire carries a current of 2 amps. How many electrons pass a given point in this wire in 1 second? Special note, they want to know electrons, and when you use the equation, what you'll actually solve for first is coulombs. So you'll need to do a conversion at the end to convert the coulombs into a number of electrons. But first, solve for this. So starting from the equation I is delta Q over T, I'm going to rearrange to solve for delta Q. So the delta Q is going to be I times T, and I'm ready to plug in now. It's easy to see that the amount of charge that passes the given point is going to be 2.0 coulombs. So something else I just got from the reference table is that 1 coulomb is equal to 6.25 by 10 to the 18th elementary charges. We're going to use that to convert. So I set up a conversion factor here with those two values. 1 coulomb is equal to 6.25 by 10 to the 18 elementary charges. And I could have chosen to put the 6.25 in the denominator, but I put it in the numerator so that I could have the denominator for coulombs, which is great because it's going to be able to cancel the coulomb from the initial information. So yeah, those two cancel, and I'll just need to multiply the 2.0 by the 6.25 to get the number of elementary charges. So I just ran that through a calculator. I got 1.25 by 10 to the 19th elementary charges. All right, so we do need to know the conditions that must be necessary in order to have a current flowing along a wire. So the basics here are that in addition to having a complete circuit or a closed loop, you also need to have a difference in potential between 2 points in the circuit. So what they're really talking about here is voltage, that you need to have a potential difference. And that potential difference is either going to be provided by a cell or a battery. Here's what a cell would be symbolized to look like on your reference table, and here's what a battery would look like in terms of symbols, both of which are going to provide the voltage or the potential difference necessary to produce a current. All right, and then we would measure that potential difference using a voltmeter. The symbol for that is going to be a V in a circle along a wire. So there's a little bit more to this idea of current. Positive charges will actually move from higher potential to lower potential, which is the positive potential to the negative potential, meaning that the positive charges move from the positive part of the battery to the negative part of the battery. Alternatively, if you were going to define this in terms of negatives, the negative charges would move from the negative to the positive. So when we describe the direction of a current, it could be defined literally in either way, but most currents consist of electrons in motion, not protons. So since most currents consist of electrons, we naturally choose the electron flow as the direction of current, which means negative to positive. So here's my check-in question. Which condition must exist between 2 points in a conductor in order to maintain a flow of charge? And this would be the one that would be in addition to having a closed loop. So in addition to a closed loop, you would need a potential difference or voltage. All right, so conductivity in solids. Not all solids can conduct electricity. The easiest way to think about this is just to consider that metals have the best conductivity. Non-metals, however, would be the opposite of conductors. We would call those guys insulators. So metals are good conductors mostly because of the way their electrons are arranged in the atom. Metals have something called a mobile sea of electrons, and the mobile sea of electrons allows the electrons to move around freely, which also makes the metal able to conduct electricity. So in addition to just metals, we also have this situation which deals with dissolved ions. An ion is a charged atom, so it's not unlike an electron, but it's a whole atom that has a charge. And when they're dissolved, they're able to like sort of float around and flow and swap positions. And so what you've really got here is charges that are able to move, sort of like the mobile sea of electrons. So these mobile charges in the dissolved ions are also able to conduct electricity. All right, so here's an equation that you're going to use a ton in this unit. It is called Ohm's law if you're a certain kind of person, but if you're another kind of person, it's just the resistance equation. So resistance is a property that any conductor would have, and the way you calculate it is relatively simple. It's a ratio of the voltage in the battery for the circuit over the current flowing through the circuit. So you just take that voltage and divide it by that current, and you'll get resistance. The unit is a really fun unit called an ohm. The unit for that, or the symbol, kind of looks like a horseshoe turned upside down. And it is a derived SI unit, and it would just mean volts per amp. The resistance is going to, whatever you find for the resistance, it's going to be true for all points in the circuit. So let's try this question. A student measures a current of 0.1 amp through a lamp connected by short wires to a 12-volt source. What is the resistance of the lamp? So let's start with Ohm's law. So the voltage was stated as 12 volts, and the current was 0.10 amps. When you divide those two, you're essentially multiplying 12 by 10 when you divide it by 0.1. So you're going to get 120 ohms as your answer. So that's the resistance for this circuit. All right, so I'm going to do this sample problem for you guys. It starts out like this. A resistor was held at constant temperature in an operating electric circuit. A student measured the current through the resistor and the potential difference across it. The measurements are shown in the data table below. So I'm just going to plot these currents and these voltages on the graph. It's currently already labeled, and I'll just plot these data points in, and then we'll start working on these tasks and this one. So the first thing I needed to do was plot a reasonable scale on the x-axis, so I did that. Basically, just to let you in on the way I do this, I just look at the maximum value and I count the number of tick marks that go across the bottom, and I just do a little bit of division to make sure that I can get my maximum value into the number of tick marks with equal spacing between. And I was able to get the 0.050 up to here, and I just went the extra mile here, but I won't use that data. So I'm going to go ahead and start plotting all these data points now. So I got those in. So far I have marked an appropriate scale on the axis labeled current A. I have plotted the data points, and now I need to draw the line or curve of best fit. So the line or curve of best fit needs to connect as many data points as possible, but it does not need to include every data point. And I'll go ahead and do that now. It looks like this is a direct relationship. Does not look like it's too hard. So I'm going to go ahead and curve these points. So I think that's the best scenario there. And using your graph, let's find the slope of the best fit line. So slope, as you know, is rise over run. And the rise that I'm finding in my data is going to be from 12.7 down to 2.3, or I guess I should say the reverse, from 2.3 up to 12.7. So there it is. And my run is going to be from 0.05 down to 0.01. Let me run that calculation. For the rise, I got 10.4, and for the run, I'm getting 0.040. So the slope itself will be a whopping 260 volts per amp. I did throw that unit in there because the rise would have been in volts. That's this guy, and the run would have been in amps, which is this guy, so volts per amp. And so I've gotten that part done. I found the slope, but I do have to do part C, identify the physical quantity represented by the slope of the graph. So take a look at this equation. This is the one that we refer to as Ohm's law, and it says that R is V over I. If you're paying really close attention, you would know that the V is what we had down here as our rise, so there it is, and the I, or the current, is what we have up here as our run. So this here, the volts per amp, matches up perfectly with volts per amp in the equation, and that means that the physical quantity represented by the slope is actually resistance, measured in ohms. So done. All right, so factors that affect the resistance of a conductor. There are several factors. What I should start with is right here. The resistance of a conducting wire increases with the increasing length of a wire, meaning the longer the wire becomes, the more resistance you'll find. Or in other words, resistance is directly proportional to length. The reason why this makes sense is because the electrons have to flow through the wire. The longer the wire is, the more atoms those electrons are going to bump into, and the more atoms those electrons bump into, the more resistance you'll find. But there's more to it than just that. As the thickness of a wire decreases, there are fewer spaces in the cross-section through which electrons can travel. That is, the resistance of a wire varies inversely with its cross-sectional area. You can see that in the diagram here, where we have a thicker wire and a thinner wire. In the thinner wire, you can only fit just a few electrons going through at a time, and they will be bumping into atoms along their way. And in the thicker wire, we have a lot more electrons which are able to fit into a lot more spaces. So more electrons, more spaces, and you're going to have a lot more current that's able to flow with less resistance. So the prompt down here says that we need to calculate the difference in the cross-sectional areas and resistances of the two wires, assuming that the thinner wire has half the diameter of the other. So resistance of a wire varies inversely with cross-sectional area, or more specifically, I guess we could say that resistance is directly proportional to the ratio 1 over A. So I'm going to start there. So I have a ratio set up for the thin wire and the thick wire. I'm going to need to calculate their areas because I just noticed in the question that it actually only said that we have half the diameter, which is not exactly the same thing as area. So I'm going to use this equation down here to calculate the areas based on the diameters. So for the thin wire, it was stated that we have half the diameter of the other, which would also mean that you have half the radius. So I plugged that in there, and let me do the calculation. And I can see that having half the radius is going to give me actually a quarter of the area of the original, and that's because the 1/2 will be squared, so that's going to give you 1/4. So I can bring that up to the second part of the calculation, which is to compare their resistances, and I'll need to put a 1/4 in front of the area as I just determined, and that's going to give you exactly 4 times the resistance. So let me just sum this all up. the thinner wire will have 4 times the resistance and 1/4 the area of the thicker wire. When I do questions like this, it always makes me think about the difference between the types of wires that power my refrigerator versus the type of wire that powers, let's say, my iPhone. And they're very different in their lengths and in their thicknesses. Like the types of wires that power things like toaster ovens and refrigerators are very short and very thick. And we're sort of talking about both of these ideas here. The shorter the length, the less resistance, and the thicker the wire, the thicker the wire, the less resistance. So that's why the cords that power the most powerful devices in my home have very short and very thick wires. On the other hand, the devices that use the least power, like let's say my iPhone, can have quite long wires that are very thin. And that's because the resistance would be higher in those wires, but it's sort of nicer to deal with those longer, thinner wires in your life. All right, so these animations down here will not be able to work in this presentation, but I can show you in class. And basically, one of them is higher temperature than the other, meaning that the particles are vibrating much faster and they're providing more resistance. So the more vibration of the atoms in the wire, the more interference there will be with the flow of electrons, which would mean more resistance. So hotter wires have more resistance. All right. We have a equation that can sort of meld a lot of these ideas together, but we'll also need to address this idea of something called resistivity. Resistivity is a characteristic of a material, and it's intrinsic to the material. And when I say intrinsic, I mean that it belongs to the material. It's not based on outside influences. So basically, some metals are better conductors than others because their resistivity is lower. So the lower the resistivity, the lower the resistance. And you can see that here in the equation. Here's resistivity. It's symbolized by the Greek letter rho. I know it looks like an italics P, but this is actually a Greek letter. And there's a direct relationship between resistivity and resistance. So the larger the resistivity, I think you can see, would be the larger the resistance. Additionally, the larger the length of the wire, the larger the resistance, but we knew that from the previous slide. And we also know that the smaller the area, the more resistance there will be. That's an inverse relationship, because when area goes down, resistance goes up. But you could also just say that the larger the area, the less resistance, and it's also inverse. So that's just our way of combining all these factors. The only thing that's been left out is temperature, and there are equations that exist that will include temperature, but the way we're getting around it here is that all the resistivities that are listed on your reference table are for exactly 20 degrees Celsius. So that means that all of the questions that we'll solve here are based on a single temperature at 20 degrees Celsius. All right, let's calculate the resistance of a 4-meter length of copper wire having a diameter of 2 millimeters, and let's assume the temperature is 20 degrees Celsius, which means that we'll be able to use our reference table. So R is rho L over A, let me add that in. So since this equation is set up correctly, we don't need to adjust it. Let's just plug in values. The rho, or the resistivity for the substance copper at 20 Celsius, is 1.72 by 10 to the negative 8 ohm meters. The length of the wire is 4 meters. And it's worth mentioning that if the question gives you a length in centimeters or millimeters, that you would need to convert to meters. All right, and it says that it has a diameter of 2 millimeters, which is not at all the same thing as area. So when we do this area, it is going to need to be in square meters, so we're going to have to convert this 2 millimeter diameter to meters first and then create an area. So check out this equation. Area is pi r squared, and we'll use the pi button on our calculators in a second, but the radius would be 1 millimeter, and we need to convert the 1 millimeter into meters. So a millimeter is 1,000th of a meter, and you can also find that on the front page of your reference table. So I'm going to write in 10 to the negative 3 and then a square. So I got that, and that means that the value for area is going to be 3.14 times 10 to the negative 6 square meters. So I'll use that and I'll plug it in to my area in the denominator. And as you guys know, I like to separate the multipliers from the exponents. So in my first step, I'm going to do 1.72 times 4 divided by 3.14. I got 2.19 times 10 to the, and I can figure that out by looking at just the exponents only. So in this case, I'm going to do a negative 8, and I'm going to subtract from that a negative 6. Since negative 8 minus negative 6 is the same thing as negative 8 plus 6, I got negative 2. So my answer is going to be 2.19 times 10 to the negative 2. And this is resistance, so the unit is ohm. And that is my final answer, 2.19 times 10 to the negative 2 ohm. Alright, so with that we have reached our pair up. I will make copies of this. You don't need to copy this down, so I'll make copies of this for you guys. And of course this is our summary. And thanks for watching, and have a great weekend.